And so number 3, the graph of the continuous function g, the derivative of the function f is shown above or below. It's down over here. The function g is piecewise linear from -5 to 3, and g of x is equal to that from 3 to 6. So we have two different parts of it. One of them is the graph and its lines, and the other part is this little parabola here. If f of 1 equals 3, what is the value of f of -5? And let's see, g is the derivative of f. So that means f of x will equal the integral of g. All right, and if we want to know f of -5, well, it'd be from whatever value we want to x, of g of x dx. So that means if we want to find f of -5, one way we could do that is we could go maybe from 1 to -5 or from -5 to 1. Doesn't make a difference really. So we could say the integral from -5 to 1 of g of x dx equals f of 1 minus f of -5. All right, so now we can solve this for f of -5. Just maybe we can add this one over and subtract this one over. I don't know, a couple different ways to do that. But either way, we get f of -5 equals, so if we added this one over, subtract that, we'd get f of 1 minus the integral from -5 to 1 of g of x dx. I suppose I shouldn't have used x here when I wrote this. T, how about that? T. I always forget to use a different variable when I write that. All right, so this integral here is just the area under the curve from -5 to 1. So from -5 to 1, we want that area, and then we're going to subtract that area from f of 1, which we know is 3. So this is 3 minus, and then we're going to find this area. So we're going to break it up into shapes that we know. So like from here over to here, it's just a rectangle. Actually, it's a square. Its height is 3, its width is 3, so this area is -9. Here we've got a little triangle. So it's a 1 by 3, and it is negative. I mean, you can say that that's -3 if you want. And so that'd be -3/2. Right? 1/2, 3, -3 times 1. Then we've got this little triangle here. Like this little section is 0, so don't have to worry about that. This little triangle here is 2 by 1. So this is 1 times 2, and half of that would be 1. So we've got this -9. We've got this -3/2, and we've got this +1, right? And that's basically our answer. Well, yeah, that's basically our answer right there, which is a matter of working that out. So we could distribute this plus, 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 minus. Let's see. So we got 3 plus 9 is 12, minus 1 is 11, plus 1.5 would be 12.5, I think. How'd I do? All right, so they wrote it as a fraction, but that is 12.5. Yep, that works. So we had the integral. Basically, they wrote that, which is the same thing we wrote, and the answer. Yep, there we go. All right, part B. Let's switch colors up here so we know it's a different part. So part B, evaluate the integral from 1 to 6 of g of x. Well, that shouldn't be so bad. We just want the area under the curve, then from 1 to 6. So we're going from 1, which is right here, all the way to 6, which is right here. All right, so if we start that, well, we're going to break it up into a couple shapes. So first of all, like from here to here, like this section, it's just this little box here, and it's 2 by 2. All right, so really we're saying it's going to be the integral from 1 to 3 of g of x dx, plus the integral from 3 to 6, the rest of the way, of g of x dx. From 1 to 3, it's that box. It's 2 by 2, so that is just 4. No sense writing it out and working it out. It's just what's the area of that box? The area of that box is 4. From 3 to 6, it's this parabolic function. So we're going to plug in this function right here. So the integral from 3 to 6 of 2 times x minus 4 squared dx. And we're going to integrate that. So we got a couple of different ways we can integrate it. We could square it out and then just integrate it and do that. We could pull the 2 out front and then just kind of ignore the 2 while we're integrating. And we could do substitution with u is x minus 4 and du is dx. So we're going to end up getting the integral of u squared du with the 2 out front. I'm leaving off the bounds because I didn't switch the bounds over. All right, we could just switch the bounds over. It's not really a big deal, but we're going to get 2u cubed over 3. And then we switch back to x's. So there'd be 2/3 x minus 4. And then we put the bounds back from 3 to 6. Cubed 3 to 6. So now we're plugging 6 in there, and then we're plugging 3 in there. So we get 2/3. 6 minus 4 is 2. 2 to the third is 8. Minus plug in 3. We're getting -1. -1 cubed is still -1, like that. So that gives us 9 in there. So 2/3 of 9, that's going to cancel. We get 6. So we're getting 4 from this guy. We're getting 6 from that guy. So 4 plus 6 gives us 10 as our answer. And Ryan is here. One of the Ryan H's. There we go. All right, how'd I do on that one? Hey, look, I got the right answer. So we split at 3, that is 1 point. So we split it up into the 2 separate integrals. That's 1 point right there. We're doing the antiderivative of this guy. So in other words, we got this part right here. That's also 1 point. And then getting the actual answer in the end is another 1 point for that problem. So that was 3 total points. All right, part C. So let's see, from -5 to 6, on what open intervals is any, if any, is the graph of f both increasing and concave up? Give reasons for your answer. All right, so if f is going to be increasing, so this is C, that means f prime of x needs to be greater than 0, but f prime is equal to g, the derivative of the function f. So in other words, g of x just needs to be greater than 0. So if we want to look, where's g of x greater than 0? Well, it's from here onward, basically. So that gives us x is greater than 0, right? 0 to 6, I guess, or I should specifically say. So 0 is less than x is less than 6. If you want to put equal to there, you can. It doesn't make a difference. All right, but from 0 to 6, f is increasing. All right, just because g is positive. All right, next, if we want to know where f is concave up, that means f double prime is greater than 0, which means, well, if f prime was g, then f double prime is g prime. Needs to be greater than 0. All right, well, that tells us g prime is greater than 0 whenever g of x is increasing. So we want to know, where is g going up? All right, well, if we look at the curve, it's going up from here to here. Then it's flat. Then it's going down. And then it's going up from 4 on to 6. So it looks like it's increasing from, let's see, 0 to 1 and from 4 to 6. All right, so if we're asking, and it specifically says open intervals, so we should probably just leave them open here instead of including endpoints. Give a reason for your answer. So where is it both increasing and concave up? Well, from basically these intervals right here. All right, so f is increasing and concave up on 0 to 1 and 4 to 6, since f prime is greater than 0 and f double prime is greater than 0 on those intervals. Well, let's see. Maybe I did it right. Yeah, no, 0 to 1 and 4 to 6. All right, so now we're not looking at the concavity of this actual graph here, because remember, this is the derivative. This is already f prime. So if we want f double prime, it's just whether or not it's increasing or decreasing. So this graph is telling us where it's positive and negative pretty easily just by looking at it. Above the axis, it's positive. Below the axis, it's negative. When it's 0, it's 0. Yeah. So that means f double prime is where this is increasing and where this is decreasing. So like flat, this means f double prime. Let's just do it in a different color here. So for like f double prime, we'd have 0, and then it's increasing here, so it's positive. Then we have this 0 section, then it's increasing here, so it's positive. Then we have this other flat section, so it's 0. Then it's decreasing, so then it's negative, and then it's increasing, so that means it's going to be positive. Can I go back to A and B when I'm done? This A and B right here, real quick, you mean? All right, cool. All right, so let's see, backwards. And we need to do part D. So let's see, I need another color and I just used purple. I like my purple. We'll go with green. Find the x coordinate of each point of inflection of the graph of f. Give a reason for your answer. Well, actually, we just kind of did that. Point of inflection, though, would be a point where it changes signs. So we're looking for a point where the graph of f is going to change inflections. All right, so for D, we need f double prime to change from f double prime greater than 0 to f double prime less than 0 at a point. All right, so we just went through and did the signs here just a second ago when I was going over that. So when it's flat, it's actually 0. So like this isn't going to be a point. This is going to be a long stretch here. And then we're positive. So then we'd be concave up. And if we want, I can just go ahead and write out the whole number line chart here thing. I don't know where I'm going to end up putting it. Actually, I don't even need arrows at the end. It stops at -5 and stops at 6. All right, so let's see. It starts out, I probably didn't need to make it this long, but from -5 all the way to -2, it's just 0. And then from -2 to -1, it's positive. Like the graph is going up, so it's positive. And then from -1 to 0, it's flat again, so it's 0. And then from 0 to 1, it's positive again because the graph is going up. And then from 1 to 3, it's 0 again because it's flat. And then from 3 to 4, it's negative because it's going down. And then from 4 to 6, it's positive because it's going up. So this has no concavity. It's going to be a straight line, basically. This has concave up. This has no concavity. This is concave up. This has no concavity. This is concave down, and this is concave up. So the only place it changes concavity is at x equals 4. So x equals 4 is our point of inflection because we have a change in concavity right there. Change in sign of f double prime. All right, so let's see. What did they say? The graph of f has a point of inflection at x equals 4 because f prime equals g changes from decreasing to increasing at x equals 4. So we have our answer at 4, and we have some sort of reason because we showed the concavity here and said that we had a change in concavity because of that. All right, so that one was a little tricky. This is actually all A-B problem. Like there was nothing in this problem that was a BC level concept. Like oftentimes the questions will be the same between the two exams. You guys will just have an extra added part sometimes, but in this one, there was no extra added part. All right, number 4. So number 4 was a bit trickier, if I remember. So the height of a tree at any time t is given by a twice differentiable function h, where h of t is measured in meters and t is measured in years. Select values of h of t are given in the table. I don't know if you guys have noticed, but like these table problems come up a lot. Use the data in the table to estimate h prime of 6. Using correct units, interpret the meaning of h prime of 6 in the context of this problem. So let's see, h prime of 6. So that'd be when t equals 6, which would be right here between 5 and 7. So what we want to do is we want to basically find the slope between those 2 points. So for part A, h prime of 6 is equal to the slope between, and you wouldn't necessarily have to write this out, but the first point would be 5, 6, and the second point would be 7, 11. And I probably shouldn't say equal. I should say approximated by, roughly equal to the slope between those two. That's what we're going to use to approximate it. So it's approximately going to be equal to 11 minus 6 over 7 minus 5. So that's what, 5/2 or 2.5. And using correct units, interpret the meaning. So this was meters per year. So at time t equals 6 years, the tree's height, because that's what h is measuring, height is changing at roughly 2.5 meters per year. So we have to say at that time, and then that's what's happening. The height is changing because that is the h prime. It's the rate of change in height. Or the rate of, you could also say the rate of change of height at year 6 is approximately 2.5 meters per year. You could also write it in the fraction. You could say 5 meters every 2 years or something like that. H prime is the rate at which okay, so they just said what H prime meant. They didn't even say that's the 5 halves per year, but we've got it. So we've got the estimate of 5 halves, and we've got the interpretation with units in meters per year. There it is right there. All right, part B. Let me change colors here. Sure, red. Explain why there must be at least one time t between 2 and 10 such that h prime of t equals 2. All right, well, we're basically looking for any 2 points here such that the slope between those 2 points will be 2. And then we can say, oh, by the mean value theorem, it's basically going to happen. So we can try and go from 2 all the way to 10 and see if the slope between those two is 2. But this 1.5 and 15, that's not going to give us a nice 2. So if we look between these two, so that's a change in 1, that's a change in a half, that doesn't give us 2. If we look between these two, that's a change in 2, that's a change in 4, that will give us a 2. So from the 0.32 to the 0.56, the slope is 6 minus 2 over 5 minus 3, 4 over 2, 2. All right, so do they say by the mean value theorem or do they say by something else? All right, so that's what they're using. The point, so h is differentiable and it's continuous. So by the mean value theorem, there exists a c such that h prime of c equals 2. Yep, that's what they used. Okay. All right, so those are the 2 conditions we need for the mean value theorem. So in order to do the mean value theorem, we need to say that h is continuous and that h is differentiable. And this is, again, on the interval from 2 to 5, because that's what we're talking about, on 2 to 5, on 2 to 5. So by the mean value theorem, h prime of x equals 2 for some 2 is less than x is less than 5, some x value between 2 and 5. All right, so that's just a straight up application of the mean value theorem. All right, part C, they love to ask this, to use some sort of integration property to find the whatever the area is, whatever the area means here. They love to ask that stuff. So use a trapezoidal sum, okay, with 4 subintervals, all right, indicated by the data in the table to approximate the average height of the tree over the time interval from 2 to 10. So the average value is basically what it's asking us to find. All right, so remember, average value is 1 over b minus a. So 1 over 10 minus 2, then it's going to be the integral from 2 to 10 of whatever the function is, h of t dt. All right, so now, so this is going to be what, 1/8? And this integral is approximately equal to, and we're going to use the trapezoid rule. And it said 4 subintervals. Well, here they are. 1, 2, 3, 4. Wow, it's amazing how that worked out perfectly, how they had it set up there. So the first one has a width of 1 times, and then it's the average of the 2 heights. All right, it's just how the trapezoid rule works. So 1.5 plus 2 over 2. Plus the next one, let's see, we're going from 3 to 5, so its width is 2. And then the heights are 2 and 6. So 2 plus 6 over 2. I started to write 4, I don't know why. All right, and the next one, we're going from 5 to 7, so that's another 2. And let's see, the heights there are 6 and 11. So 6 plus 11 over 2. Plus the next one, has a width of 3. So that's 3 times the heights there are 11 and 15. So 11 plus 15 divided by 2. And whatever that works out to is going to be our guy. You can actually leave it like that on the AP exam. Like that is fully worked out as far as they're concerned. If you want to continue to work it out, you can. Let's see what it works out to. So we've got our 1/8 out front there because it said the average value. And then it's got this guy, yep, that guy, yep, there's the times 2, that guy, there's the times 2, and that guy, there's the times 3. All right, they worked it out and said 65.75, or as a fraction, it's that. I mean, that seems like a lot of extra work to me, but look at what they said they give you the points for. Trapezoidal sum, that's this part right here, that's 1 point, and approximation. Well, look, with the 1/8 out in front, that's the approximation. So that's full credit right there. All right, so don't waste your time trying to work out anything nasty like that on the AP exam when you can just write that and be like, boom, there's the answer right there. All right, now let's take a look at part D. So the height of the tree in meters can also be modeled by the function g, given by g of x is that. So this is the height in meters, where x is the diameter of the base of the tree in meters. When the tree is 50 meters tall, so that's a g, the diameter of the base of the tree is increasing at a rate of that many meters per year. All right, so that is a dx dt. That's a change in the diameter, and x is the diameter. And somebody else is here now. Attendance, there we go. According to this model, what is the rate of change in the height? So that's dg dt with respect to time, dt, in meters per year at the time when the tree is 50 meters tall. All right, so somebody left and came back for just a second there. So what we want to do, g of x equals 100x over 1 plus x, is we want to take derivatives of everything with respect to time. So implicitly with respect to time. So that means this would be not g prime, but dg dt. In this, x is a variable with respect to t. We've got to do a quotient rule. So it's bottom times derivative of the top. And we took the derivative of x here, we actually get a dx dt. Minus the top times the derivative of the bottom. Derivative of the bottom, derivative of 1 is 0, derivative of x is dx dt. All over the bottom squared. All right, now, do we have everything? Let's see. We've got g is 50. We've got dx dt is 0.03. What about x? We need x, right? There's an x here, there's an x here, there's an x here. We definitely need to know x. All right, and we're trying to get dg dt, so this is what we're trying to solve for. All right, so we got to be able to get x some way. Well, they told you g is 50, and here's another formula right here that involves g and x. So 50 equals 100x over 1 plus x. So now we want to try and solve that. So we're just going to multiply this up. 50 times 1 plus x equals 100x. Distribute the 50. Subtract the 50. Oh, and look, this is working out real nice. Divide both sides by 50. X is just 1. Cool how that works. And that's in years, so that'd be 1 year. So that means dg dt is equal to 1 plus 1, so 2 times 100 times dx dt, which was 0.03, minus 100 times x, which is 1, times dx dt, which is 0.03, over 1 plus 1 is 2 squared, so over 4. All right, now we could probably work that out because 100 times 0.03 is just 3. 2 times 3 is 6. And this is 100 times 0.03 is 3 over 4, like that. Don't want to get those two mixed up. So this is 3/4. So dg dt is 3/4. And g stood for the height. So this is meters, height in meters. And our time was year. So let's see, did they want us to explain it or just find it? According to this model, what is the rate of change of the height of the tree with respect to time? Okay, in meters per year at the time when the tree is 50 meters tall. So if we want to make sure we get the point here, we can say at the time when the tree is 50 meters tall, the rate of change in the height is 3/4 a meter per year. Like, you can say that if you want. I don't think you need to. I think if you wrote that, that is probably plenty. Let's see what they say as far as scoring goes. All right, so it got its own page. So let's see, they didn't even show the work for that. They just said g of x equals 50, so that means x equals 1. Didn't need to see that work. All right, so you get 2 points for taking the derivative of g implicitly. So 2 points for getting basically that guy right there. And they have the xdt off to the end instead of right here and right here. Honestly, I would rather see it right here and right here. So it should be there and it should be there. All right, but whatever, it doesn't make a difference really. They simplified the derivative. You don't need to simplify the derivative. All right, and then 1 point for the answer. There's our answer. And you get a max of a 3rd point if no change. So if you left off the xct, you could get 1 out of the 3 points. I'm not sure which one of the point you would get. Maybe 1 for doing this part of the derivative. I don't know. But yeah, that is the point breakdown for that one. All right, and they wrote out the sentence like a good boy, but they don't have to do that because it didn't say to interpret it. All right, so that is that. And let's move over to wherever there the multiple choice here are. So let's see, we had 5 people miss this one, so we're half and half here. Area between curves. It'd be nice if more than 10 people were doing these, but 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we got 11 people here, so at least one of you didn't do it. What is the area of the region in the first quadrant bounded on the left by the graph of that and on the right by the graph of that? All right, so let's see, do they give the answers in terms of integrals or is it just not going to show up? Oh, they actually give you answers. Okay. So we've got a couple of things we can do here. And yeah, they actually find where they cross. I don't know if you really need to do that. I guess you probably do if it's bounded by that on the left and that on the right. So yeah, the first thing you're going to need to do is find, and this one's a good bit of work, find where these two functions equal each other to figure out where they cross. Go back to a through c, not in a moment. Y equals, or actually no, 2y is this guy, equals y times the square root of y to the 4th plus 1. All right, you can do this on your calculator, and you probably should, and we get y equals 0 as one answer, and we get y equals 1.316 as the other answer. All right, once we get those two answers, it tells us that this guy is on the left, and that means this guy is on the right. So that means when you're integrating, you kind of turn your head sideways and look at the graph. All right, the one that's farther over to the right is the one that goes on top. So 2y is going to look, let's see, that'd be y equals x over 2. So it's going to look like that. This other guy, I don't know what he looks like, but he's probably going to look something like that. Who knows? All right, so they're going to cross at 1.316 and 0. So that means we're going to be integrating from 0 to 1.316 with 2y minus this guy, y times the square root of y to the 4th plus 1 dy. Now, typing that in your calculator, you can just pretend everything is x. You can just type in x all you want in the calculator instead of y. That's probably what they do. So yeah, the graphing calculator is used to evaluate the definite integral. Yeah, because you're not going to be able to do that by hand. You definitely have to use your graphing calculator to do that one. Or something called trig substitution, but yeah. And that's what we get the first guy up there. All right, this is definitely a trickier one. Whenever they want us to integrate with respect to y instead of x, we kind of turn our head sideways, and it's a tougher problem to do. I understand. All right, so that's that one. Let's see, what else did we struggle with? I think the next one had 6. Oh, there's 6 people missed this one. And yeah, Caitlin, I'll go back in the end here. Base of the solid region in the first quadrant is bounded by the x and y axis, and the graph of y equals that. For the solid, each cross section perpendicular to the x-axis is a rectangle whose height is 3 times the width. What is the volume of the solid? So the x and y axis and the graph of that. All right, so we would probably want to take a look at the graph of that so we can just have an idea of what that graph looks like, which you're probably going to want to use the calculator to take a look at. And where is my calculator? There's my calculator. It does exist. It just isn't on. So y equals, I have to turn that plot off too. So we've got x minus 2 squared. That's not squared. Now it's to the 21st. There we go. Divided by, and we want to divide by all of this. So 2 times x plus 1. Close that parentheses. Close the other parentheses. Let's zoom 6 here. So it looks like this little section right in here is all we're really looking at right there, from there to there. All right, so let's zoom. Well, actually, let's just change the window. So we're going to go from 0 to maybe 5. Yeah, we don't have to go down very far. -1 maybe, and maybe up to 5. And there it is, and it's definitely crossing at 2 right there. So it looks like we're going from 0 to 2. And the height of this is just this y. And we're doing rectangular cross sections coming out of this. So we want to, basically, we're looking at this section. Oh, let's see if I can get it a little bigger. Window. So I only need to go up to 3 and maybe up to 3 there, and that'll help. Trying to make it a little bigger. All right, so we're making cross sections coming out of this guy. So this is one of our cross section, and that's just y. And then it says we're coming up and it's 3 times the width. So when we're come up to make our cross section, we're making 3y. So it's y times 3y, so it's 3y squared is what we want to integrate. And we're going to integrate from 0 to 2. All right, so we're integrating from 0 to 2 along the x-axis, dx. But now we've got to plug that in for the y. So we got the integral from 0 to 2 of 3. Then this guy, x minus 2 squared over 2 x plus 1. And then the whole thing here is squared dx, like that. And then it's just a matter of throwing it in your calculator and getting this answer here. So it was math 9 to integrate. And let's see, did they do the same thing? Yep, they did the same thing. There it is right there. There's the integral. Look at that. I can still do these. Yay! I haven't done calculus since you guys have done calculus last. You're like, Robeson, that's not promising. It's not reassuring you here. All right, so let's see. We've got this one and this one. So 2 left to look at. Particle motion. Oh boy. I haven't used calculus in the grocery store. I'm saying I haven't been to the grocery store. That's what it is. Haven't been to the grocery store. This is just answer B. Thanks, guys. Oh, it takes so long for these problems to load here. All right, so over the time interval from 0 to 8, a particle moves along the x-axis. All right, so it's just moving along the x-axis, so it's just moving side to side. All right, yeah, online shopping, exactly. The graph of the particle's velocity at time t, v of t, is shown in the figure above. So this is velocity as it's moving along the x-axis. So when it's above here, then it's moving to the right. When it's negative here, that means it's moving to the left, and so on. Over the time interval from 0 to 8, the particle's displacement is 100 units to the right, and the particle travels a total distance of 1,875. Okay, so we don't really have a y-axis here, so that's good information. What's the total distance the particle travels while moving to the left? I'm not sure how they went about doing this. Let's see. So distance and displacement, they'd both be integrals. One of them is absolute value, one of them is not. Oh, so those two integrals should be canceling each other out for the most part and leaving us with 100. So, yep. Let's see, what did they go about doing? So the integral from 0 to 8 of the velocity is just 100. And that's the part, and that's the displacement. The integral from 0 to 8 of the absolute value is 1875. Solving this system gives that. Oh gosh, they set up a system equation. So we have some motion to the right, some motion to the left, I guess is what they're doing. And this is motion to the right, motion to the left. But since it's the total distance traveled, it doesn't matter which one's positive and which is negative because it's just total amount of motion. All right. And when they solve that system, they get that. So that would be when it's moving to the left. That's a tricky little guy there. And that, of course, would be the integral from 1 to 5, where it was below the x-axis here. That's a neat little thing. I don't know if I would have thought to do it that way with the system of equations. So let me try explaining it again. So the integral from 0 to 8 of the velocity, this is the displacement. It ends up equaling 100. Part of that is moving to the right, and part of that is canceled out by moving to the left. I can't erase. It doesn't like to let me erase with my pen. I have one click erasing on everything else except for here. So this is moving to the right, and this is moving to the left. All right. The next thing we've got is the total distance it travels. So moving to the right counts as total distance, and moving to the left counts as total distance. And that's the integral from 0 to 8 of the absolute value of the velocity. Absolute value. I suppose I should put a dt here too. And that equals 1875, which is a plus b, because both of those will be treated as positive. And now we get this system of equations that we want to solve, right? It's not so bad to solve it. We can just add the b over here. We get a equals 100 plus b. Then we can take that and plug it in right there. So we get 1875 equals 100 plus b plus another b. We can subtract the 100. 1775 equals 2b. Divide by 2. And that's where they're getting 887.5 as b. And b is what we wanted, the amount of time it's moving, or the amount of distance it travels to the left. That one was that's a good one. I like that. I've never seen one like that before. I like that. Having to set up the two equations and solve. Should be a fun one. All right, and one more here. And which one was it? No, there's two more towards the end here that aren't good either. Functions of y. Yeah, we don't like these functions of y, do we? All right, so let R be the region in the first quadrant bounded by the graphs of x equals y to the third. So that's the curve. So this is x equals y to the third. And x equals 4y. So that's the line. That's linear. As shown in the figure above, what is the area of R? All right, well, looks like they cross at 2. I mean, we could check that if we wanted to. We set them equal to each other, but they are going to cross at 2 because 2 to the third is 8 and 4 times 2 is also 8. So they cross at 2, 8. Right? There are several ways you can do this. So if you want, one way would be to integrate, and this would be the top function. This would be the bottom function. So this is x equals 4y, and this is x equals y to the third. So we'd go from 0 to 2 along the y-axis of 4y minus y to the third dy. That would be one way to do it. Another way to do it would be to solve for y, because I know that's what you're more used to. Right? So if we solve for y, we'd get y equals the cubed root of x. And this one we'd get y equals x over 4. And if we went across this way, and then we'd be going up and down here, we're going to 8. So from 0 to 8, this is now the top curve, the cubed root of x, minus the bottom curve, which is x over 4 dx. So we can set it up either way. Both of these integrals should give us the same answer, which looks like it's just 4. Let's see, which way did they go with? Oh, they actually showed both. So here's the first one, 4y minus y to the third from 0 to 2. Because the line would be the curve on the top. If you, again, turn your head that way and look at it, the one on top is the one that's farther to the right. Or you could solve for y on each one of them, and then you're going along the x-axis from 0 to 8. And then the cube root of x is on top, and the x minus 4, the line would be on bottom, because then up is high and down is low. All right, so that's that one. And let's see, what else do we have? There was the 2 at the end, right? Yep. Volume of cross sections. Volume of cross sections is always a little odd. So the base of a solid is a triangular region in the first quadrant bounded by the graph of y equals 5 minus 3/5 x. The y-axis, the x-axis. For the solid, each cross section perpendicular to the x-axis is a square. What is the volume of the solid? All right, that's not so bad. So this is just a line going down. So like if we drew this, it's going to cross at 5, and it's just going to go down like that. And if we plugged in 3, I think that's the other place where it's going to equal 0. So it's going to look like that. And we got cross sections coming out. So perpendicular to the x-axis. So that's perpendicular to the x-axis. These cross sections come out at you. And this y is the same as that y, because they're squares. And this y is equal to 5 minus 5/3 x. So the area of this is y squared. So we're integrating, and these little squares go from 0 to 3. So we're going from 0 to 3 of y squared dx. And now we say y is just this guy. So we get the integral from 0 to 3 of 5 minus 5/3 x squared dx. And then it's just a matter of working that out. So there's a couple different ways we can work it out. So it looks like they worked it out by hand. Maybe this wasn't a calculator question. If it was a calculator question, we could just throw this right in our calculator and get an answer. Looks like it's a nice whole number. So they're squaring that out. We get 25 minus 50/3 x plus 25/9 x squared. So then we get an x here. We get x squared over 2 here. The 2 gives us the 6 down there. X cubed over 3, so that gives us 27 down there. And then we're plugging in, technically they should probably have parentheses in front there. Plugging in 3 minus plugging in 0. Plugging in 0 gives us 0. So we really just have to plug in 3. If we plug in 3, we're getting all that. And it's just a matter of working it out. Looks like a lot of the fractions are going to cancel out, and we just do get 25. All right. I'm more interested in can you set up the integrals than work out the integrals, because setting them up is usually the hard part. Is he going to go to the next question or not? There we go. All right, so last one here, and we'll call it quits, and then I got to try and upload the videos, and I'll go back and show you the A through C, Caitlin. Let the region R in the first quadrant bounded by the graphs y equals 1 minus x to the third and y equals 1 minus x. So 1 minus x to the third is going to be the curved one. And the straight line is going to be y equals 1 minus x because it's linear. As shown in the figure above, the region R is the solid, the base of a solid. For the solid, each cross section perpendicular to the x-axis is a square. So perpendicular to the x-axis means going this way. We're making squares. They're going to come out at you. I'm going to go out that direction. So this distance here is going to be the same as this distance here because it's a square. So this distance here is the top curve minus the bottom curve. So this is going to be 1 minus x to the third minus 1 minus x. So 1 minus x to the third minus 1 minus negative x. So it's going to be plus x. The ones are going to cancel. We're going to get x minus x to the third for that side. So that means this side is also going to be x minus x to the third. So that means the area of this guy is going to be area equals x minus x to the third squared. So that means if we want to make this a solid, you know, each one's going to have a little dx. So we'd be integrating from 0 where they cross here to 1 where they cross here. So it'd be the integral from 0 to 1 of x minus x to the third squared dx. And now it's just a matter of squaring this guy out. So that's x squared minus 2 x times x is, so that's x to the fourth plus x cubed times x cubed is x to the sixth. We want to integrate that from 0 to 1 dx. So this is going to be x cubed over 3, 2x to the fifth over 5, x to the seventh over 7. From 0 to 1, plug in 0 is going to give us 0. Plug in 1, we get 1/3 minus 2/5 plus 1/7. And then it's just a matter of getting common denominators and trying to put all that together. It looks like 8 over 105 is what we end up getting, which is not really an easy fraction to get to there. They just magically jump from this to that. Okay. Yeah. But yeah, they've got the 1/7, they got the minus 2/5, they got the plus 1/3. And I am confident that you guys could get to 8 over 105 from that somehow, magically, maybe. Yeah, multiply this one by 35, multiply this one by 21, multiply this one by 15. I think that gets us there. Yeah, that should get us there. Yeah. All right, so there's our answer. And we'll